Let our vector function fxy equal to xy squared. Find the work done by our vector function f in moving a particle counterclockwise along the arc of the unit circle from 0, 1 to -1. Recall that work is going to be equal to our integral of the vector function dotted with dr along our curve C. Our curve is given by the unit circle from the point 0, 1 to -1, 0. So it looks like this right here, -1, 0, and this is 0, 1 over here. And we're moving counterclockwise. So we are moving in this direction. We must first parametrize our curve. Right now, the unit circle represented in Cartesian coordinates is going to be equal to x squared plus y squared is equal to 1. However, if we parametrize this to get a vector function r of t, it's going to be equal to cosine t sine t, where our t goes from pi over 2 to -pi. So now that we have our curve, let's start finding the integrand. dr is going to be equal to our derivative of our vector function r of t. So the derivative of cosine t is negative sine t, and the derivative of sine t is cosine t. And let's put our dt. Now that we found our dr, let's find our big F, which is going to be equal to f of r of t. Our vector function f is defined by x, y squared, but if we plug in our r of t, we are going to get f of r of t is equal to cosine t sine squared t, because our y value here is squared and our y value for r is sine, so just sine squared. Now that we have our key parts for our integral, let's begin evaluating it. To evaluate this, let's first start taking the dot product of f dot dr. So we can have cosine t sine squared t dotted with negative sine t cosine t. The dot product is fairly simple. We just take our cosine and our negative sine, multiply them together, which is going to be equal to negative sine t cosine t plus our sine squared t times the cosine squared t. Let's factor out our cosine. So then on the inside, we're just left with negative sine t plus sine squared t. Now that we have our integrand, let's plug in our bounds. So we have from pi over 2 to -pi, and let's put our cosine negative sine t plus sine squared t. And don't forget our dt. To evaluate this integral, let's perform a u substitution. Let our u equal to sine t, making our derivative of that equal to cosine t dt. Now let's change our bounds. So sine of pi over 2 is equal to 1, and sine of -pi is going to be equal to 0. So our new integral goes from 1 to 0, and after performing our u substitution, we're just left with negative u plus u squared du. Now that this is a simple integral to solve, let's first change the order to make it easier to understand. From 0 to 1, we can switch it to become 0 to 1, but have a negative. That is an integral property. And let's change u squared to minus u. Now if we evaluate our integral, we will have u cubed over 3 minus u squared over 2. And our u's go from 0 to 1. Plugging this in, we're going to have negative. We're going to have 1/3 minus 1/2. And finally, that will evaluate to negative 1/6. Our negative on the outside is going to make this positive 1/6. So, the work done from moving a particle counterclockwise along the unit circle from 0, 1 to negative 1 is equal to 1/6.